Welcome geniuses, I'm Genie, your best buddy for A-levels. In this channel, we'll bring you to explore the secret formula behind success.
For this question, if they ask you which type of wave can the Doppler shift be observed, the answer will be definitely A, because all types of waves can undergo Doppler effect. That means sound, light, and all those can still undergo Doppler effect. For this question, they gave you the ambulance which is traveling along a straight road with this speed. It then emits a siren sound of this frequency. Now the speed of sound is given. So the ambulance passes a man standing at the side of the road. So what is the frequency of the sound heard by the man as the ambulance moves towards and away? So don't worry, the formula is given in your data sheet as this. So if you want to know which to use, plus or minus, you must remember that when the ambulance comes towards the man, the waves will bunch up. So the frequency, the observed frequency will be higher because the wavelength is shorter. So when it comes towards the man, you must use minus at the bottom, so the bottom is smaller, so that this ratio will be more than 1 and your observed frequency will be bigger than your source frequency. But when the ambulance leaves the man, then you must use plus, because the bottom must be bigger than the top, then your ratio will be less than 1, so then your observed frequency will be less than your source frequency. So let's substitute V here as the speed of the wave, which is the speed of the sound, and the Vs is the speed of the ambulance. Alright, so the speed of the ambulance or the speed of the source is given as 30 meters per second. So you just substitute plus and minus, you get these two. So don't forget, when it's coming, the ambulance is moving towards the man, you'll be higher frequency. Alright, and when it's leaving, you'll be a lower frequency. Alright, so the answer will be donkey. Alright. But I also want to make a point to show you that if you were to take this and this frequency, which are the two new frequencies, and you subtract your original frequency, you notice that the difference will be 190 for this and the difference will be 160. So for this one, you have to take 2000 minus 1840. For this one is 2190 minus 2000. You're taking the bigger minus the smaller just to see the magnitude of the change. So you notice the magnitude of the change is not the same, even though the speed approaching and leaving is the same. Alright, so remember, it's not symmetrical, so you don't calculate one side and then you assume the other side will just be symmetrical, just one side plus 190, the other side minus 190, so that is wrong. Now for the first part, to define the frequency of a sound wave, remember the frequency is referring to the oscillations, number of oscillations of the particles, right? So the correct answer will be number of oscillations of a particle per unit time. Now things that they will not accept is instead of saying per unit time, you say in unit time. That is wrong. You cannot say that. And other things is you cannot say is number of waves per unit time. That is also wrong. So it's not the number of waves, but it is the number of oscillations of the particle. Right, the part B, a sound wave travels through air, so describe the motion of the air particles relative to direction of travel. So the way to answer is to say that the direction of oscillation of the air particles is parallel to the direction of travel. So what you can say is oscillations or back and forth motion of the particles. But if you just say that the particles move parallel to the direction of wave travel, that will be wrong. So you must mention what kind of movement. Now the next part, they gave you the CRO, trace on the CRO, and they gave you the time base and the y-axis setting. So let's find the frequency. So to find the frequency, we have to use the time axis, right? So we need to find the time taken for one oscillation, which is the period, and then from there you can find the frequency. So the time taken for one oscillation, which is from here to here, is 1, 2, 3, 4 of these boxes, where one box is considered to be 5 small boxes. So therefore, if you remember, one of these box here, which is this one, is 1 centimeters. So there are basically 4 centimeters here. So the total time will be 4 centimeters, which is from here to here, multiplied by your time base, 0.5 millisecond per centimeter. So 1 over that, you will get your frequency. Now for the next one, when they said the horn of the car sounds continuously, what will happen to the trace seen on the CRO when the car travels at constant speed directly towards the stationary microphone? So we know that Doppler's effect will occur when the car travels towards the microphone, the frequency will increase. So the question is, what will you see on the CRO, right? The changes to the trace on the CRO. So because the frequency is higher, yours is a time base, so the period will be shorter. So you can say the period will be shorter, or you can say the peaks are closer together, also can. But what you cannot see, or what you cannot say, is your wave fronts are closer together. So wave fronts, no, because you do not see the wave fronts. Wave fronts would refer to the wave that you are observing, but what you are seeing is the trace on the CRO, which is the voltage. So you should not say wave fronts. But there's also another thing that not many people realize. If the car comes towards the microphone, the sound will be louder as well. So there's a third mark here for mentioning the amplitude change here and here. So for this part, the amplitude will be larger. So you need to say the amplitude increases. For the next part, where the car moves directly away from the microphone, then what will happen is the frequency will decrease. So what you will observe is the period will increase. So the correct answer is to say the period increases, but you can say that the waves will be further apart. Alright, but of course the better one to say is the period. And another one is you should mention, right, is the amplitude. So the amplitude will be smaller, because as the car moves away, the amplitude will be smaller as it will sound softer. But many students, right, what they did was they made a mistake here and here. They talk about the frequency. They said here the frequency increases, here the frequency decreases. Now the answer is not wrong per se, but because it does not answer the changes to the trace, you can't see the higher or lower frequency here, but you can see a shorter period and a longer period. So in this question, we have a particular wavelength emitted from the sun, but at any instant, the band of wavelengths that you observe ranges from less than this to more than this. So what could be the explanation for this Doppler effect? So remember, if it is more than this, means the frequency is lower than the source frequency. So if it is higher wavelength, it means it's a smaller frequency. So smaller frequency means the sun must be moving away from the earth. But when your wavelength is less than this, that means your wavelength is smaller, so the frequency will be higher than the source frequency. That means the sun must be moving towards the earth. So how can the sun be moving away and also moving towards the earth at the same time? So you can explain this if you consider that the sun is rotating. So the top part of the sun, when it rotates this way, it will be moving towards the earth. So therefore this part will produce a higher frequency, which is a smaller wavelength. And this portion, as it rotates, will be like going away from the earth. So therefore it will produce a lower frequency. That means the wavelength will be more than this. So therefore the answer would be the sun is rotating. Now for this question, when the car is moving in a straight line towards an observer, they said that the observer measures the frequency of the sound from the engine. So when the car approaches, he hears this frequency, moves away, he hears this frequency, and they give you the speed of sound in the air. So what is the speed of the car? Now this is obviously Doppler's effect, so you can use this formula, but the problem is this, right? You have the observed frequency in both cases. You also know the speed of the sound, which is the speed of the wave, but you do not know two things. You don't know how fast the car is moving, which is what you need to calculate, and also you don't know what's the original frequency of the car. Alright, so how are you going to solve this? So you notice you got two unknowns, so you're going to solve simultaneous equation. So you can substitute the first case here, when the frequency is higher because the car approaches, so this will be a higher frequency, so you must use the minus Vs here. So you substitute your observed frequency, the speed of the sound, and the two unknowns here. Then you cross multiply and you form an equation. At the same time, you would substitute the lower frequency and you must use plus here. So then again, you cross multiply and find the second equation. Alright, here. So you solve these two equations simultaneously using your calculator if you know how to, and you'll be able to get the Vs and the Fs. And then you will get a Vs as 34, and then you will also get the Fs as 198. So since we are finding the speed of the car, which is 34, alright?
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.